Welcome, everybody. Glad everyone's here. Welcome to Science Futures. Actually, can you hear me without a mic? I just feel like I speak better without a mic. Okay, I'll do that then. And same goes for you, Joshua, if you don't want to use a mic. Yeah, so before introducing Joshua, I just want to say a few words about the series for those who weren't here last time. So what Science Futures is, what our aspirations are, and what's coming up in our events calendar. So first of all, I'm Eric. Hi, nice to meet everyone. I am not a scientist. I am a historian, actually, and I guess a theorist. I also run the London Night Cafe, which is a third space project nearby. But I do think a lot about sort of how scientists and other talented people throughout history have sort of found ways to increase their agency, and how communities come together to form institutions and sort of shape the containers in which other people act. So that's why I'm here and why I've gotten involved. And also, this is Ed. So Ed runs Newspeak House. That's the place we're in right now. This fantastic space. And it's also home, by the way, to the London College of Political Technology, which is also upstairs. So it's a residential college, essentially, with 8 to 12 very talented fellows who live here for a year, and they work on various projects, usually hovering around the intersection between civics and tech, because it's a political technologist college and community. So what Science Futures is. So Science Futures is a transdisciplinary exploration of transformative science, engineering, and other research. So we're aiming to create this sort of platform and a community for people who are excited about shaping the future and who are eager to find each other to collaborate in doing so. We believe that it's essential to think about the future very actively, and that we should be building preferable futures. And science and technology are really crucial here because they refuse to just take things as they are, as a given. They're really excited about changing what's possible. They're also some of the best means available to us to increase our agency over our lives and over the environments in which we live. But at the same time, science and engineering need an impetus behind them, a motivation and a direction for exploration. We think that this is something that transdisciplinarity can really help with, drawing upon different subject areas and methods to determine the directions that innovation goes. So a bit about our aspirations. So this is already getting at our aspirations, but in short, we're looking to help catalyze the connections and collaborations that can make London a key center of innovation in the world. We think London is extremely well positioned to play this role for a variety of reasons. So the UK itself is taking bold steps towards becoming a leader in scientific innovation, with organizations like ARIA, which funds us to do these events, funding moonshot science projects and research. The UK is also innovating on climate. You may have seen that Keir Starmer recently announced that the UK wants to cut its 1990s emissions by 81% by 2035. And we don't yet know how the next few years are going to go, but our last event was late October. We've since had an election in the United States, where I'm from, and it seems likely that the next 4 years will be very turbulent for science in the United States. We don't know exactly how that's going to play, but there's quite an anti-science atmosphere around this administration that's coming in. I don't want to be super partisan about it, but it seems likely that a lot of federal agencies are going to be cut, and there's going to be all this talent that's sort of cut loose. And there's no reason why that talent can't land in London. But in any case, we think that the UK should be proactive in competing for science and engineering talent, and reversing the so-called brain drain that leads ambitious people away from here. And there's a lot that needs to happen to make that possible. And we hope that a sort of transdisciplinary movement can start to get some of that stuff going. So just want to acknowledge there's a severe housing crisis here. There's a related affordability crisis. There are not just enough actual spaces like this to go to and sort of come together. London is very expensive and very difficult and really dominated by really concentrated real estate interests. And so it can just be hard to get people in the same room working on the same stuff. But that's one of the things we want to try to work on, is mobilizing people to build those kinds of projects. So we at Science Futures are really drawing inspiration from places and times where groups of people gathered and revolutionized our society in some enduring way. So we're trying to understand and hopefully eventually replicate some of the things that made these centers of innovation possible. And we're not just talking about Silicon Valley. We're really excited about places like Bloomsbury Square, the Chelsea Hotel in New York, the CCRU in Warwick in the 90s, progressive reform in New England in the 1880s and 90s, the World's Columbian Exposition in 1893, Jena, Germany in the late 18th century, LaRouche in Paris, et cetera, et cetera. There are all these moments when like people were just like, I was there in that really important moment. We feel like London could be one of those things in the 20s and 30s. So that's our inspiration and our aspiration. It's obviously not something we can do alone, but we do want to build this sort of buzzing community of people. And yeah, there's ways that you can get involved. So first of all, please get in touch with us if this excites you. Follow the Discord, follow the WhatsApp, get on our calendar, on Luma. If you're working on something related to science, engineering, and/or futurism, please introduce yourself, not just us, to each other as well. We're looking for people who are interested in meta science too. So people who are thinking about the meanings, methods, and missions of science. If that's you, please get in touch. We're also looking into setting up transdisciplinary science, engineering, and/or futurist houses. Think of intentional communities that maybe host events and have a bunch of people working together on various projects. If you're excited about that, or people are working on that, please also get in touch about that. We really want to help sort of facilitate those connections and catalyze that stuff. And finally, if you are an experienced researcher or someone who's working on something that pertains to reshaping the future in some meaningful way, again, please get in touch with us. Just a bit about what's coming up on our events calendar. So there will be the first Meta Science meetup this Sunday. That'll be at the London Night Cafe. And yeah, then there's also, after that, on Wednesday, the 27th, going to be a Finish That Manuscript sort of collective writing session. It'll basically be a bunch of people writing together and holding themselves accountable to getting their manuscripts written. So if you're working on some writing projects of some kind, I know most of us probably are in one way or another, please come to that too, if you're available. Anyway, now I'm going to introduce Joshua. So Joshua Becker is an associate professor at the University College London, is a volunteer lecturer here at Newspeak House, and is a volunteer mediator with Calm London. Joshua also serves as a co-chair for the Collective Intelligence Conference, is an associate editor for the Collective Intelligence Journal, is a contributing member to the Collective Learning Network, and is a mandolin player for the Leaf Sheep Collective. 4 collectives that you're involved with. At present, Joshua is particularly focused on how groups can make decisions amidst disagreement and why they can fail to reach agreement, even when it would benefit all members. And we wanted to hear from Joshua today because they work on such an important and persistent problem, the coordination of groups and of group action. In a world where the future of life on this planet is literally threatened by humanity's struggle to make collective decisions, we thought that Joshua's work would be a perfect subject for our second ever Science Futures talk. So please help me in join me in welcoming Joshua Becker, who will be presenting Collectives, Intelligence, and Me, Putting the Science in Social Science. Sorry, one other thing. You're going to take Q&A at a few different intervals in your talk, right?
Yeah, so this talk is broken up into 5 sections. It'll be very obvious. I'm going to pause between sections and invite questions or comments or discussion. I can't talk very long. I start to lose my voice. So hopefully that'll make things a little more interesting for you too. All right, so I'm actually not going to talk a ton about collective intelligence tonight. I'm going to talk about collective intelligence, but mostly I'm going to talk about how I research collective intelligence. But before I even get into that, I want to talk a little bit about science. Joking, I want to talk a lot about science, but I want to talk about questions first. This is a question: what is ethical, or as Plato might have asked, what is virtue? I just want you to raise your hand if there's a correct answer to this question. Okay, a couple hands. How about, this is in the wrong order here, but how about what is love? Raise your hand if there's a correct answer to the question, what is love? Wow, more than what is ethical. I guess I am going in the right order. Okay, how about if I asked you, what is science? Is there a correct answer to this question? Some hands, okay, more. Okay. How about if I ask the question, what is gravity? Is there a correct answer to this question? Lots of hands. All right, I'm going to say there's no answer to any of these questions. These are, I would argue, poorly formed questions. Whenever you start a conversation with what is blank, you're actually not asking about a thing at all. These are just words, right? So what is blue? What is light? What is the sky? These are not really questions we can ask, and if you go to early efforts in science, they spend a lot of time asking these types of questions. They don't really get you anywhere. They're fun, they're great for a Friday night, but it's Tuesday. We can ask questions like, why is the sky blue? So we can, that's an observable phenomenon. We can look up and we can argue why we call it blue and what different colors are, but why is the sky that particular color? So all of the initial questions I started with are essentially what I would call a categorical error. They're not pragmatic, they're not scientific, they're not answerable questions. But this is phenomena driven. We start with an observation. There's something we see concretely in front of us, and then we can ask, what's going on here? Why is it happening? How is it happening? So science is phenomena driven, but it's also very much funding driven. So I'm going to talk a little bit about Newton tonight. I don't know anything about Newton's life. I've read some of his life physics, but I'm going to make a wild guess that Newton was paid for the military benefits of his work, right? If you're trying to figure out where to aim a cannon, understanding the basic physics of projectiles is very useful. And all these problems that Eric mentioned tonight are really important, tangible problems, some better funded than others, but this is, very much what drives research, the grants people apply for. So it's phenomena driven, but we have practical goals we're trying to accomplish. So, why is the sky blue? Because the plane is invisible, because someone got some really good cloaking technology. That's an answer to why is the sky blue. Or something about fragments of light. I'm not a physicist. So what do we want to do? We want engineering. And I'm not a physicist, so I'm not trying to engineer planes. We want to engineer social systems, right? So we care about things like improving housing, reaching net zero. So we want to do things in the realm of collective intelligence. We have a design team. Maybe they're trying to design a solution to the housing crisis. We want to help that design team be more creative. That's an engineering problem that we can potentially solve. We don't really have to, I do like collectives, so I put in all my collective stuff in the bio, but we can't really ask what are collectives. We already learned that that's a trick, but we can say we've got a collective in front of us. How can we help this collective do what we want it to do? So how can we help this team be more creative? How can we help an organization to reduce churn in their employees or their volunteers or their customers, right? These are engineering problems. How can we organize social systems to reduce carbon emissions? All engineering problems. So what I'm going to talk about tonight, I'm going to start by defining the problem. That's what I'm doing right now. So for me, the problem is, how do we engineer social systems? Or how do we think about engineering social systems? I'm going to spend a good bit of time talking about how science works. This is very much my take on it. Other people are going to have different takes. That's okay. I'm going to spend a good bit of time talking about how social science works, gradually getting more controversial. Again, this is my take on it. Other people doing different things. That's okay. I'm going to give an example, modeling group decisions. So this is where the collective intelligence comes in. It'll all be very simple by the time we get here, because you all already know how to do science and how to do social science. So we'll just breeze through this in a couple minutes. Then I'm going to wrap up by talking about what I think this means for the future of social science. And so the focal problem I'm going to talk about tonight, Eric mentioned it. I'm very interested in how you can use a committee or a team or a group of people sitting around a table. I'm very interested in how groups can reach agreement on a complex decision. So this is the engineering problem. The question I can ask is, why do they sometimes fail to reach agreement? And that's a phenomenon right in front of me. We see it happen all the time. Groups fail to reach agreement, and later they say, oh, if only we had had this idea, it would have been perfect. So that is my engineering problem. All right, so essentially the world has problems, and we are aiming to come up with solutions. All right, so I'm going to pause there for a minute. That's step one. Any questions or comments? All right, I'm going to take a sip of my water while you think about that. Was there half a hand? Yeah.
I have a bit of issue with the use of the word engineering.
Sure.
In my mind, it's
besides science is a big problem? Yeah, so I wouldn't put science and engineering separate at all. For me, science is in service of engineering, and engineering requires science. You're going to use a lot of the similar methods. Terminology is always going to be a little bit problematic. So let's see what I do with it, and then we can circle back around and ask Ali how you feel about that later. Yeah.
You can think of engineering as a form of design as well.
Yeah, sure.
And from that point of view,
yeah, very good. And what I'm eventually going to get to is science is how we come up with models of understanding the world, and engineering is what we do with those models. So they really are two sides of the same coin, very much the same practice. Other questions or comments before we move on? All right. So how science works according to me. All right, so it's not asking these deep philosophical questions, what is gravity? It's starting with an observation, hey, I dropped this apple and it falls. And then saying, okay, why does it fall? Coming up with an explanation. And then using that explanation, which is a model, it's how we think about the world, how we organize the world, to come up with a prediction. And so the observation is going to be data. So when we're talking about science, there's always data. It can be informal. I'm observing things right now and I'm getting data into my brain. It can be experimental data. It can be carefully collected ethnographic field data, right? There's a lot of different ways of getting observations about the world. So that's it. Observation is data. The explanation is a model. The explanation is a claim about how the world works. This can be verbal. This can be mathematized. It can be computational. I'm going to get into that in a little bit. A lot of different ways to do explanation as a model. And then the prediction is going to do two things. So you're going to predict the prior observation. I've seen apples fall before, so I'm predicting why they fall. I'm explaining, right? But it's like I can drop another apple and it's still going to fall. That's prediction. Also predicting future observations, including repetition. So I'm going to drop the apple again, as well as different things. Now I'm going to drop an orange. Now I'm going to drop a feather. Now I'm going to drop an anvil, right? So out of sample and out of distribution prediction. So that's essentially what we're doing. We're starting with observations. We're trying to explain why they happen. And we're using those explanations to generate predictions, including both of things that have already happened, as well as things that haven't happened yet. So this is the start. We start with observations, which is data. And where does that data come from? So a lot of that data can come from observatories. And I'm using this in this super generic term. I don't mean just astronomical observatories. Observatories being anything you set up to sit and observe things. So examples could be a telescope. We're observing the world. Could be a microscope. I'm observing something real tiny in my lab, but I'm just watching it go. Could be a binoculars. I'm sitting in the park and observing people, right? Participant observation. I'm just going to go and embed and live in a community for a while and get my observations through conversation eyes. All sorts of ways of getting data. This is not really so much controlled data. You're just looking out in the world and observing. That's it. And then, of course, we also have laboratories. Laboratories being places that are like very controlled observatories. There's not really like a super fundamental, universal philosophical distinction between these things. Again, these are words. The world didn't exist in perfect order to spawn these words. We use these words to try to describe our world. So when I talk about laboratories, I'm talking about trying to observe things under more controlled conditions. And generally that means being able to repeat it over and over again. So I'm going to talk more later about I'm going to talk now about what exactly is an experiment. So laboratories are where you do experiments. Experiment, very simply, something you can repeat. An experimental trial. We talk a lot about randomized controlled experiments where you're like manipulating different outcomes, but it doesn't have to be. An experiment can be, I dropped this feather and it fell slowly. I dropped this feather again, fell slowly again. I dropped this feather again. 100% of the times I dropped the feather, it fell slower than the bowling ball, right? So that would be a great example of an experiment. So I'm going to talk about now a few experiments. Aristotle dropped feathers and bowling balls. I assume Aristotle had bowling balls, and concluded that lighter things fall slower than heavier things. Very reasonable. I'm going to talk about an experiment. Millikan oil drop measured electromagnetic strength of electrons just by watching little oil drops go up and down in a magnetic field over and over again and measuring them really carefully. Very observational, but it's experimental because he's controlling it and replicating it and repeating it. In social science, anybody here ever hear of 6 degrees of separation? Yeah, it's a Kevin Bacon movie. Also, it's an experiment done in like the 60s or 70s. This sociologist, Stanley Milgram, just mailed a bunch of letters to people and said, hey, try to get this to someone in Boston, and saw what happened. It was an experiment. You could repeat that over and over. So lots of different ways of getting data about the world. So I want to give a bit of an example of this now in practice with physics. I'm not a physicist, but I talk a lot about it because it helps me think about how science works. So we are interested in firing cannonballs at our enemies. So we're very interested in understanding how projectiles move. So Aristotle had this model of how things move and fall, and his model is that, this is Aristotle's theory, things go to their natural place in the world. It's a good model, things go to their natural place, not very formalized. It makes a prediction, feathers fall slow, bowling balls fall fast. Bowling balls have more stuff, so they want to be closer to the other stuff. Perfectly valid scientific theory. A decent approximation. Feathers do fall slower than bowling balls, right? Decent approximation. So this is an example of a verbal model, very, very common in social science, and then it has predictions. So then we've got Galileo. Galileo says, wait a minute, actually things all fall at the same speed in a vacuum. I'm not sure how he figured it out, but he figured it out somehow, and he said, okay, so I have this model actually, instead of different gravity for different weighted things, everything follows constant gravity. So when I throw my football or my baseball, it's under constant gravity, and I can derive from that, he's doing some mathemagic, a prediction that when you throw a ball or fire a cannonball, it's gonna go in a parabola. A decent approximation of the world, but not that accurate, right? It's accurate if you're really small. A parabola is pretty good. But in fact, Newton came along and said, the closer you get to the Earth, the stronger the gravity pulls. The further you get, the weaker the gravity is. So it's variable. This doesn't matter if I'm throwing a baseball, but it matters if I'm launching an intercontinental ballistic missile, right? Ballistic meaning not fired under, not under its own power. And it turns out if you actually account for this extra detail about the slight variation in gravity, it's not quite a parabola, it's a hyperbola or an ellipse, depending on the velocity, or a parabola under extremely specific circumstances. So what we see here is, verbal model, prediction, decently accurate, formalized mathematical model, simplified assumptions, decently accurate, more detailed assumptions, more assumptions. And then if you get really into it, you go past Newton, you realize that we don't even live in a normal Euclidean geometric world. Everything you learned in geometry class is wrong. Parallel lines get closer, they just never touch. We live in a hyperbolic world. This is like Einstein and relativity. Point is, we live in this world of just increasingly decent approximations. That is what science is doing. So I want to give a couple more examples of this. This is kind of the detailed example. Here's another one. Mendel was an early geneticist, I guess. I don't know all the terms of fields. Mendel was breeding pea plants and started with 50-50 purple and white pea plants and observed, these are purebred purple and purebred white, observed that when you mix purple and white flowers, you get all purple flowers. That's kind of nutty, right? Then when you mix those purple flowers, you get 75% purple and 25% white, very regularly, very predictably. This is an observation. Then Mendel comes up with this model that there are recessive and dominant traits, and if you have one of each, you get the dominant one. If you have two recessive and so forth, you get the recessive, and if you have two dominant, you get the dominant. And you can use this model to derive, formally, very simple algebra, this prediction that at equilibrium, you'll get the 75% purple, and you can predict all this other stuff along the way. So this is another example of an observation, a model, a prediction. I just wanted to give you something outside of physics. Here's another one. Here's a brief one. More physics. An observation, this is Millikan with the oil drops. Basically, he's trying to figure out how much charge an electron has. So it comes up with a very clever experiment. We know the strength of gravity on an oil drop suspended between an electromagnetic field. So when you get the electromagnetic field just right, that the oil drop doesn't move, you know the electromagnetic strength cancels out the gravity, so you can figure out the electromagnetic field of an electron. So he did this. And then people have continued to do this and continued to refine the measurement. They get this super detailed exact measurement of the electromagnetic charge of an electron. So the model is nobody knows. Nobody knows why an electron has that particular charge. I assume someday, 100 years, 10,000 years, someone will figure it out. But I just want to point that, you know, even physics has things where it's just, I don't know, that's just the way it is, that's just love, that's just virtue, right? All right. So these are some examples of the observation, the model, the prediction. I talked about Newton figuring out the parabola, the hyperbola and ellipse thing, Galileo figuring out the parabola. Anybody know what math you need to figure that out? Yeah. Yeah, it's sort of calculus. It actually goes way older than calculus. So I want to talk about math for a minute. Apollonius, one of the ancient Greeks, just did all this crazy geometry, imagining that you have a cone and you're slicing it at all different angles and what shapes does it make. That turns out to be parabolas, hyperbolas, circles, ellipses, and you can describe it using calculus. So, but the point is that if Apollonius hadn't done this thousands of years ago, then Newton would not have been able to figure out the hyperbola ellipse thing. So we need math in order to analyze our theories. So you start with it, I'll get more into this, I'm going to get gradually more into all of this, but you need math in order to analyze our theories. So math becomes useful. Apollonius didn't, as far as I know, do anything particularly useful with these conic sections. It was like for the love of the universe, trying to divine the, you know, the beauty of truth or whatever. But math becomes useful when it turns out that the structures of math are isomorphic, the same shape as the structures of our world. So hey, it turns out that when you throw a ball, it flies in the shape of the same thing that happens when you slice down a cone and cut off the edge and look at the shape, right? I don't really know why. It doesn't matter. It's useful. It works for us. So that's where math comes in. I don't do math. It's not the only way to come up with formal theory. I have some proof. I have one paper with a proof, and I do a lot of computer simulations. So I want to talk now a little bit about what we're doing with that math, or those computer models, or those simulations. So I want to talk about formal theory, right? We started with Aristotle saying things fall because they want to go to rest at their natural place. Heavy things, lots of stuff, be close to the earth. Light things want to be close to the heavens, and they all sort to their natural place. So this is a theory. It's a model with a prediction. It's an explanation. It's verbal. So when I say theory, what I mean is explanation. That's it. There are two words that more or less, to me, mean the same thing. And when I talk about explanation or theory, what I mean is a model plus a prediction, right? So the model isn't necessarily the prediction. The model for Newton is that as things move away, the gravity gets weaker with the inverse of the square. Then you take those assumptions, that model, and you say, okay, what can I figure out about if this is true, what then is true? You're deriving implications of the model using math. So we can analyze data. We can also analyze models. So we've got verbal models, we've got mathematical models. I want to talk specifically about formal models and what makes them, to me, kind of special. So my read of the history of science is that things become useful. Theories become useful when they are formalized. Aristotle's theory with the feathers and the bowling balls, not super useful for building machinery or engineering social systems or anything, but it's a good start, right? We got to get somewhere and then we can increasingly approximate it. So yeah, that's formal theory. So what I mean by formal theory is that, well, the conclusions derive necessarily or logically, formally, or mathematically, or computationally from the assumptions. So I start with my assumptions. This is how, you know, there's dominant and recessive genes, or there's this rule about gravity, or there's this rule about social networks, and I derive some conclusions from that. So the model is my setup, and the predictions are what I derive from that model, and then the theory or the explanation is all of that stuck together. And math is very useful for formal theory, but it's not the only way to do formal theory. And as we already covered, there's a lot of different ways to do math for the same thing. You can do calculus, you can do Euclidean style geometry, you can do other stuff that I don't know about because I'm not a mathematician. Okay, so one last piece of how science works, data analysis. This is the part that's really cool. Well, it's all really cool. Everything I'm going to say is the part that's really cool. Data analysis. So how did Galileo actually test whether objects moved in a parabola? He can derive it mathematically. He can say, look, I believe that everything falls at the same constant rate, or accelerates at the same constant rate, 9.8 meters per second squared, derive some conclusions from that. But now how do I actually show that this is what's going on in the world? So, this is a major question of how do we do it? How do we analyze data? So you can get this data. Well, how do we even get data? So what Galileo did, which is really cool, is set some things in motion, use the math to calculate where it would land, very specific point estimate, prediction, and then so look, it lands exactly where it predicted it. So it's just this piece right here, the landing zone. You don't need the whole arc, right? You could come up with clever ways of maybe measuring an arc like a ball on a board and some ink, and he was using ink with his marbles, but the way you use theory to come up with data analysis is the theory tells you what's important, gives you predictions that you can test your outcomes against. So it all feeds in together. Data is nothing without theory. Theory doesn't come from anywhere without data, even if it's casual observation. Data is nothing without analysis. The analysis is formed by theory. So what I'm going to get to at the end is it's a big iterative circular process. And this, broadly speaking, is data science. Now you think of like data science as machine learning, but really data science is anything that you are doing with data, including thinking real hard about it. Okay, so the process of science in a nutshell. Here, the final word, once and for all, the correct answer, or one of many, for how science works. You start with an observation, a thing to be explained. Then you come up with a descriptive analysis that identifies key features of the observation. Hey, I've just been living in the world and I noticed that some things fall fast and some things fall slow, and when I throw a ball, it goes in a curve. What the hell is going on here? So I'm starting with a descriptive analysis, nothing testing any predictions. I'm just looking out in the world and describing it as I see it. A lot of social sciences are doing really important work here. Then you come up with a model. So you sit around and think, okay, I've observed this in the world. What do I think it is that's going on that's generating these things which I've observed, the key features, the curve, the landing thing. We're not worrying about like the color of the ball or the temperature or the sound it makes as it goes through the air. These are all parts of our potential data, but we're saying, look, I only care about where it lands and the trajectory that it traces while it goes. That's going to be problem driven too, right? You're trying to fire a cannon, you need to make sure it goes over the walls and lands in the right spot. Then you've got your model. You're going to use your model to generate hypotheses. So you're going to analyze your model either verbally or mathematically or computationally. You're going to generate some new hypotheses. You're going to predict the future. You're going to say, okay, I predict that if I fire this missile at this velocity, at this angle, it's going to land in this spot. And you do that a bunch of times. You go get more observations. So you've got your hypotheses. You now run your experiments, or you go out and observe more things in the wild. So you get more observations and data. And now you do your hypothesis testing analysis. Now you go back and you say, okay, is my prediction correct? And then it just cycles through that. So there's this notion that I love from social science called grounded theory, which I think is what all of science has always been doing. Grounded theory, and this is not in my methodological expertise, so apologies if I'm getting some details wrong here. The basic idea is you have some observations, maybe some participant observations, maybe some interview, you're just out in the world. You generate a theoretical model. Then you go back to your data, you compare that against your model, you do some more analysis. And so it's an iteration between the data and the theory and the data and the theory. Your theory is grounded in the data. That is what I think all of social science is doing. And it is getting us increasingly detailed approximations, isolating these specific parameters of interest, the things we care about, the things we don't care about. We focus on velocity, we ignore the color of the projectile, right? We ignore the electromagnetic pole of the projectile for now, right? We ignore the weather on the day we're doing the experiment. The basic idea is that the world is incredibly messy, the social science world quadruply so, but we can tame it through this gradual refining process. All right, so that is for me how science works. I'm going to move on, but I want to pause for a minute to invite any discussions or questions while I take a sip of water.
How's it affected when the observation is affected by process observing phenomena is affected by the observation.
Oh yeah, that's actually something I think about all the time. I wasn't really going to get into maybe the end today. That's a huge problem with social science. So I think about this a lot right now because one of the huge funding sources right now, everybody wants to fund research on AI. Someone in the UK is giving away £1 million for AI and collective intelligence. I'm like, I can't figure out what to research because whatever we do today, we can ask questions like, how do people emotionally react to AI? We've got an AI facilitator and a human facilitator doing the exact same thing. We can reasonably expect from our casual observations of the world that people will react differently. And that becomes an engineering problem. How can I design an AI if I don't know how people are going to react to it? Okay. Now I publish my paper and someone puts up the like Forbes or Harvard Business Review article, fingers crossed, on how people react to AI versus human facilitators. Then everybody goes and reads that article, and now suddenly my research is not replicable because everybody's behaving differently. This is a very real problem with social science. That's an answer to what happens is that your model sees the door. I think one of the things we can do, one of the things I try to do is I try to do research. I try to do science that's still going to be true in 100 or 1,000 years. So there are certain fundamental principles, right? There's a sort of mathematics of social science. So you can do theory that says, if people react to a facilitator this way, how does the group perform? If people react that way, how does the group perform? You get your models that can account for a lot of different potential parameters on people's behavior. You have a really complex model that accounts for a lot of different situations, and then it's true today, then it's true tomorrow, then it's true in 50 years. It's a very hand-wavy answer because I haven't lived long enough to actually try doing it yet, but I think that's what we have to do. And science just happens in different scales. Really rapid science is going on to tell us just right now, how are people using AI? Data gathering, really basic stuff, and science happens at slower scales about the fundamental cognitive processes of humans that are maybe less likely to change, but will always be shaping our reaction to AI, right? Yeah. Yes. Thank you. I really, this is good. I really want you to understand what I mean by formal model, and I apologize for not dwelling on that more. This is why we do the questions throughout. When I say formal model, first of all, what I'm contrasting that with is an informal model. So like a verbal model, a narrative model. I just kind of tell you a story. Feathers like to be close to the sky because they have heavenly qualities. Bowling balls like to be close to the ground. This is Aristotelian physics, by the way, It's a little funny to us now, but it's a way to look at the world when you don't know other stuff. So there's verbal models, very informal, very narrative. They don't really tell you exactly what your assumptions are and how your assumptions lead to the conclusions. You're not generating this story, this really detailed story. It's really hard to pin down. It's easier to say what formal models are. For me, a formal model is when you exactly and precisely specify your assumptions, also known as premises, right, at the top of your logical deduction. And then you logically derive your predictions from your assumptions. So assumption is Newton's 3 laws, force equals mass times acceleration. An object, at motion will stay in motion, right? You derive pretty much all of Newtonian physics from these 3 basic principles. And it's not a perfect, this is formal and this is informal. There can be hidden assumptions, even in mathematics, like Euclidean mathematics that says 2 parallel lines, never get closer. There were hidden assumptions in that. People cracked open some of those assumptions that actually parallel lines can get closer if they only touch at infinity and so forth. So it's not a perfect thing, but for me, what I'm looking for is just really clear explanation, logical derivation of what my predictions are. Does that help? Is there still some vagueness? There's always vagueness. All right, keep on this. If you come away with one thing, I want you to understand why I think formal models are valuable and what they are. And I guess why I think they're valuable is mostly empirical. Again, I look at the history of science. I see that science has become useful when their models are formalized. And I think part of that is because it's precision. When you give verbal models, it's like really hand-wavy and weasel words. And if I make a verbal model about feathers and bowling balls, and then you say, okay, I did an experiment. I dropped a feather and a bowling ball and they fell at the same time, and say, well, your feather obviously didn't have the heavenly quality in it, right? So they're really vague, kind of like moving target predictions, and it's harder to hold the model and theory accountable when its predictions aren't really clearly and precisely linked. All right, I'm going to push forward. Do stick with this question. if it's not clear. I'm going to talk now about specifically social science, and I'm going to give a mention to history, and I invite you to correct me if I'm not fairly framing it. So again, according to me, this is how I see social science, and I'm even going to read history against the grain. I'll talk about that in a minute. But there's a lot of social researchers who don't see themselves as scientists. They're playing a different game than me. That's fine. I still think they're useful to science, so I'm going to incorporate that into my view. Okay, so social sciences. I want to talk about social sciences broadly. So what are they? Some social sciences. Okay, we've got economics, sociology, psychology, management, comms, anthropology, history. These are all just kind of the social sciences I'm talking about. These are all different problem areas. Economists are studying economic systems, sociology are studying social systems and culture, psychology is studying individual decisions, but there's a ton of scope creep within the social sciences and they gradually expand into each other. So I can only, and then, I did my PhD in communication. I studied with a sociologist. My committee also had a psychologist on it, and now I work in the School of Management. So I'm all over the place. What they really are is distinct research traditions, different epistemic, philosophical traditions, different methodological traditions. So the disciplinary boundaries are super vague. It's a social construction. It's not like people said, what's the best way to carve up the world? No, there were just a bunch of different schools that did their thing and gradually became fields. I'm going to try to align these concepts with my view of how science happens in practice. So I'm not claiming anything essential here. So if you notice inconsistencies in the discussion of social science, again, it's because it's not like these things were created to accomplish the best division of the world. They're just independent evolution of distinct fields. A lot of different academic traditions coming together. So what I'm going to talk about represents how I, as a scientist, view the usefulness of the various outputs of other different social science fields. Now, disciplinary divisions, super vague and ambiguous. One huge thing within social science is this seeming distinction between so-called qualitative research and so-called quantitative research. I mentioned to a colleague today in the elevator, I was going to talk about qualitative research. She got a wrinkled look on her face, real concerned about what I was going to say. So hopefully this will be amenable to Jen. So briefly, what are these things? Okay, so qualitative research, for me, it's aligning a little bit with those verbal theories. The data is going to be less quantitative. It's again, it's not a super clean distinction. So what is it? It's things like ethnographies. I'm just really embedding in a group of people and trying to understand their lived experience and write down, everything I can understand from spending time with them. Interview methods. I'm really just going to talk to a lot of people, ask them a lot of questions. Again, try to maybe understand their lived experience, write down and analyze what I get. Case studies. Any kind of thing that's building a real narrative understanding of the world. These are qualitative methods, not my area of expertise. I vaguely know what they are, and I like a lot of them. I'm going to do a little bit myself. We'll talk about that later. And then quantitative research is where you get statistical analyses. So the observational data is analyzed using a regression. You go out in the world, you get a bunch of data, you run a regression on it. Experimental data is analyzed using a regression. These are just statistical techniques. You don't need to worry about them. Point is, when you hear quantitative research, you're thinking statistics. It's not a super clean distinction. There's also a lot of stuff that I would call qualitative quantitative. You get a whole bunch of text data. You got a bunch of interviews. You can analyze it as a narrative, as a person thinking real hard about it. You get 10,000 interviews. You're not really going to be able to read those through. So you use natural language processing to pull out themes and cluster things. Is that qualitative? Sort of. It's pulling out narrative ideas. It's not producing, formal testable hypotheses. Is it quantitative? Well, you're using, computational methods and quasi-statistical analyses. So, this whole space of text analysis, I think, really blurs the lines between qualitative and quantitative. And I think a really important way, because I think this is, again, sort of a category. This is not how to think about the world. Don't worry about the qualitative-quantitative divide. Think about what your problem is and what methods you want to bring to bear to resolve it. So I instead prefer to think about it in terms of the data, the analysis, and the model, right? So the data can be qualitative or quantitative. Data can be qualitative or quantitative. So field notes, a person's experience in a setting, that's qualitative data. There's nothing quantitative about just me taking notes in a paper. But in a sense, as I said, once you start digitizing this, analyzing it in scale, it becomes potentially quantitative. You can count how many times people mentioned a certain term, right? A lot of qualitative researchers are very uncomfortable about that. Personally, I think that's a tradition thing. They see this as not what we do. It's making claims to sort of epistemic rigor that we don't aspire to, right? So they stay away from even counting things. It's not everybody agrees on this. It's an open discussion. And anytime you get something sufficiently large scale, it can be quantified. And remember, this qualitative quantitative thing is a social construction. So you've got some data, analyze it however is going to best conform to your theory and answer your questions, solve your problems, and then think about the analysis. You can have a narrative analysis. I'm describing to you what's in my data and pulling out themes, and I'm just thinking real hard about it. You can have a quantitative descriptive analysis, not always hypothesis testing, no statistics. I'm just counting things and clustering things, and it's large scale, so I'm using quantitative techniques to describe what's going on. And of course, you can have hypothesis testing, sometimes statistical, sometimes not statistical, right? There's a lot of different things you can do with your analysis besides, think about the qualitative quantitative divide. And then similarly, the model, don't, worry about qualitative quantitative, just ask, how clearly specified are your assumptions? What methods are you using to derive your conclusions from the assumptions? Are you using verbal reasoning? Are you using pure logic? Are you using math? Are you using some kind of computational simulation? So this is, applying this data analysis model from how I claimed science works in general to social science to give an alternative way of thinking about things instead of the qualitative quantitative. So I want to give a little bit of a sidebar now and talk about formal models in social science. So hopefully this will help clarify some things a little bit. So this is not part of the philosophy of science today. We don't really need to do something special for social science with formal models. It's a science like any other. We have a problem, we have observations, we have data, we have theories, we have predictions. We're doing all the stuff that Newton was doing and that Galileo was doing. But people get all squirrely and weird about formal models because we have agencies and we don't like to be predicted according to fundamental laws. People treat physics as a deterministic thing. I hit the billiard ball in just the right way. It has no choice but to go into the corner pocket because I'm that good, right? But I'm a person with agency and free will, and I'm not regulated by physics. Honestly, I don't care. Those are very real things to think about and worry about, but none of it matters for my practical purposes. Because the point is, we have seen that formal models are useful in social science. I will give you some examples of my own work later today. I'm going to talk a little bit broadly about how these occur in social sciences. You might have heard of economics, hugely mathematical science, very formalized, very far from complete. There are financial models that are pretty effective at predicting really macro scale outcomes, like the effect of supply and demand on commodities prices. Apparently there's some things that are pretty good at predicting the effect of certain things on options prices. But then like a weird weather thing happens, or people get angry about something on the internet, or someone reads the article about how people react to AI, and suddenly everything performs differently. So they have some decent approximations for business as usual under very regular standard conditions, but even economics, for all its formal theory, is extremely limited in its predictive accuracy. It's a little bit like feathers fall heavier than bowling balls, but like better. It's better than that. But it's not like we can fire a projectile at Mars and have it hit exactly on. That's not how good economics is. Operations management, I don't know anything about it, but I know they use a ton of math, and that's like supply chains, logistics. How many trucks do you need here, and boats and things moving across? That's humans, that's social science, right? People involved in that. Very mathematized. I think they're pretty effective, but again, something goes wacky with the human behavioral part of it, and it all goes haywire. Sociology. So like I said, I was trained kind of in sociology. There's an emerging field of mathematical sociology, computational sociology, analytic sociology, all different terms for the same thing. Getting pretty good. This talk kind of represents that worldview. Super basic. I can predict how the trajectory of some belief accuracy will go of a group of people in a laboratory experiment with no prior contact, engaging in an extremely limited communication scenario, but we can predict what social network structures make beliefs more accurate and what social network structures make beliefs less accurate on average, right? So again, like that electron, we don't actually know that every electron has the same charge. We just know that on average, we do these statistics and we get reliable measurements for the electron. Social science is also kind of doing on average. So maybe individual electrons have free will, and it just kind of comes out in the average. Management and communication fields, super interdisciplinary, much like sociology, a lot of qualitative, a lot of quantitative, people doing formal models in them. By no means is formal theory representative of what most or even many people are doing. Then you've got anthropology, history, which I do call a social science, following in the tradition of Tolstoy, whose goal is to ask questions like, why did a million men, and it was mostly men, walk from France to Russia, the Napoleonic invasions? These are, in practice, though, a lot more like the humanities. But I will argue they are doing incredibly valuable work towards the sciences by getting crucial observations. You cannot theorize the world until you know what's out there. You cannot build formal theories until you have basic, chunked out verbal theories. And all of this so-called qualitative research is helping us to just get that basic understanding of the world so that maybe someday someone can come along and try to mathematize it or formalize it. All right, so I now want to put all of this social science stuff back into the big picture, which is how does science work? This is just a review. This is the same thing I had up here earlier. So again, with social science, is the exact same as every other science. You get some data or observation, a thing to be explained. I've noticed that a lot of times groups fail to reach agreement, even when they actually could have found something that everybody would say yes to. It can be qualitative or quantitative, right? It can be many data points with detailed observations. It can be small, it can be large scale, it can be small scale. And then we do our descriptive analysis. We're gonna figure out key features of the thing we are trying to explain. We're gonna come up with our initial model that generates the key features. We're gonna come up with some hypotheses and go out and get more observations or experiments. And then we're gonna test those hypotheses. We're going to find that some of our hypotheses work, some of them didn't work. Our model was only a rough approximation. And we're going to circle back around to the top and try to refine our model until it gets gradually more and more accurate. And I just want to close on an explicit note on the role of qualitative research. And I think about this a lot because I'm in a department where a lot of my colleagues do qualitative research. We're considering hiring some more qualitative researchers. I have some problems that can't be solved with quantitative research. So I'm going to use the methods that are useful to whatever problem is. Humanity is incredibly complex, and you have to start somewhere. And with most of what we are trying to socially engineer, with most of the things we're trying to explain, there are so many variables, so many parameters. If you try to generate a computer simulation of just this room, you're going to have like a million parameters. It's going to predict every possible thing, and you're not going to have any way of knowing which features are important, which predictions you can test, which ones you shouldn't worry about. So you can't possibly know what to formalize or quantify without knowing broadly the phenomena in general narrative terms. So what I'm essentially arguing here, not that poetry is science, because I don't think poets will necessarily identify as scientists, but poetry, the humanities, all of the various different ways of knowing and understanding our world are incredibly critical for science. All right, so I'm going to pause on that now. The remaining parts will be fairly brief. I'm going to give an example of this from my own work. I'm going to wrap up by talking about where I think the future of this will all go. I'm going to pause. I'm going to take a sip of my water. You all know the drill.
I have a question as a historian. There's this historicist school of thought. So there's different schools of thought in history. It's not like all historians don't agree with each other about how you should study history and what the significance of history is and historical insight. But there's this school of thought called historicism, which argues that you should not. So they're very much arguing against a sort of social scientific argument that you can apply laws to human behavior in different times. Their argument is different times and places are always, they're just going to be so different that you can't apply some universal law to all of them. And I think this gets at what you're saying about there's all these different parameters, and it's very, very complex and it's very, very difficult to predict. But would you argue that if you can get all of the parameters right, that then you can start to have these laws? And I guess I wonder whether laws really make sense in a world that is that complex. Like if every situation is super duper duper different, how can you apply insights from the ancient Greeks to
Yeah.
modern civilization and vice versa?
This is a great question. And what I will say about tonight's talk is that I'm optimistic. I think we have no choice but to proceed as if the world can be tamed. It's absolutely possible that what I'm dreaming of and hoping for will be ever always in the receding future, right? Like an asymptotic goal that we're never always going to aim for, never going to hit. And I think, in a sense it's true. Again, with this, people are observing the observers and the science is feeding back. I think it's absolutely true that at sort of a mid-range level, the laws, the basic economic principles that we might apply today are not guaranteed to work, or in fact, very unlikely to work in different time periods. And I think there are universal laws underneath these things. So I think of like materials science, right? Or chemistry in the laboratory, lots of different combinations, biochemistry in particular, very hard to derive from quantum physics. But we know that somewhere below all the crazy messiness of biochemistry is atomic and quantum physics that we don't yet know how is filtering up, so that there are universal laws that are generating these material-specific laws or organism-specific laws or time period-specific laws. So for example, from the social sciences, here is something which is always true in every time period. I'm going to give you a little proof. I'm not going to do the proof. I'm going to give you the model and what you can prove mathematically. Not me. Someone else did the math. I just thought it was interesting. I found it useful. It was the same shape as the problem I was trying to study. So you've got a group of people, and they're all trying to estimate how many jelly beans are in a jar, or how many jobs will this policy create, trying to come up with a really accurate number. Interesting aside, if you ask a whole lot of people the same question and take the average, actually this is an aside, here's a law. If you ask a whole lot of people and take the average answer is mathematically guaranteed to be more accurate than just a popcorn randomly selected person. Universal law, provable, true in Galton's day in 1907 when he studied it verbally, true today when people are mathematizing it. Now, will that be more accurate than an expert? I don't know. Will that be usefully accurate? I don't know, but there's a mathematical guarantee that the average is more accurate than a randomly selected person. We can go further. We can talk about the dynamics of deliberation. We can say, let's not have a conversation, and let's say that Eric talks to Edward, Edward talks to Charlie, Charlie talks to Mishka, right? Everybody's, and you can draw out maybe on the board who's talking to whom and draw a network of information flow. Networks are great because they're very mathematizable. There's a whole centuries of graph theory. So now people are really into social networks. We can draw on that math that turns out to have the same shape as social networks. So we can prove mathematically that if everybody simply revises their opinion to become some weighted average of their own opinion and the opinions of the people they're connected to, remember that social network, that A, if people keep doing that indefinitely, the group will eventually converge on a shared opinion, and B, the people who are more central in the social network, so connected to more people, will be more influential. They'll contribute more weight to that final consensus belief. That is a law of graph theory, a law of math, of statistics, of human behavior. Now, does it ever happen that people adopt weighted averages of their peers in a social network? Maybe, maybe not. My proof is true as long as my premises are true, as long as my assumptions are true. So the things that change for different time periods, for different cultures, for different materials and biological organisms are the premises, right? Now it turns out this one, the premises are pretty minimal, and the predictions I gave were sufficiently broad that I think that's largely going to hold under some select circumstances. We can actually replicate that fairly well in the laboratory. Is that anything like what this room looks like? I don't know. But if you get people doing that kind of numeric estimation task and they revise their answers in a certain way, you will always get this particular result no matter what century it is. I just don't know if you're going to be able to get people to do that in different centuries. So there are laws. Whether those laws are useful at different times is a different question. But this is sort of a fundamental thing, because the fact is that you can now take that model and put in all sorts of different weighting rules, like men are going to place more, or have more weight placed on them than women, or confident people are going to have more weight placed on them than unconfident people, tall people, short people. So now you can think about how your culture, how your time period is shaping the way people respond to each other and incorporate the beliefs. And you can use this theory and model to say, what if people reacted this way in this time period or that way in that time period. You can still use this theory and model to think things through. Is that a satisfying answer? Is this helping with the formal theory thing at all? Please bring that question back up if it's not. Okay. Maybe one last question before I get back into it. Okay, two. Yeah, go ahead.
Can we use like deductive reasoning to grab some of the laws that we have from the natural sciences and try to transpose them into the social sciences?
Do you say abductive or inductive?
Abductive.
Abductive.
So that the idea of deductive reasoning is just that you grab the first principles of fundamental laws or observations of relationships in nature, and you start looking at the behavior of, say, society or individuals in a social system, and you can try to see how, for example, thermodynamics or homeostasis exists in the context of society and how that shapes the behavior of these agents, knowing that, people seek places that are not too cold, not too hot, all these things.
Yeah, I always struggle a little bit with abduction versus induction and deduction, but the point is you can use any reasoning method you want. So I gave this nice, neat trajectory. First I do this, then I do this. It's not always going to be in this order. It's not always going to be this linear. It's not always going to be this clean. You have sparks of inspiration. Nobody really knows where those come from. Great observation that could be explained, though. I'm not going to say what is inspiration, but I'm going to say sometimes I've noticed that people suddenly get an idea. What's going on there, right? So yeah, now I would say we want to be really careful about applying metaphors, so like metaphorically applying physics and be like, oh, people are sort of like particles, or people are sort of like neurons, and therefore, we know that neurons behave this way, so maybe people behave this way. Hey, if that's useful, great. Sometimes it works, sometimes it doesn't. I would just say don't cling to it even when it stops making sense. But an example, so I actually have a paper co-authored with a physicist. Physicists are really good at figuring out the alignment of things. So they have something called the Ising model, which just figures out how magnetic particles align so they're all pointing up. That's like saying, hey, why is it or how is it that we all drive on the left side of the road and not the right side of the road? There are now laws, legislations, but these conventions emerge spontaneously, dynamically. So it turns out that the physics of molecule alignment are also useful for mathematically predicting and explaining the emergence of conventions to a point. So there was a very famous physics model that predicted if you have an established convention in a population, a society, whatever, everybody's shaking with the right hand, right? And you want to start a revolution, you want to overturn this established convention, how big of a committed minority do you need to go around shaking with the left hand, right? Now you say, look, most people just don't care, they just want to match. So if enough people start shaking with the left hand, everybody's going to start shaking with the left hand. So this physics model says, okay, we're going to use this particle model and we're going to figure out, you might think it's 50%, because once a majority is doing the left hand, everybody will switch over. Actually, it was 9.8 something percent, right? So we ran an experiment. We basically made a game where everybody converges on a convention, and then the grad students, me, come in and we're a committed minority, try to do a different convention. We couldn't do it. 10% wasn't enough. And I said 9.8, 10% should be more than enough, right? 15% was enough, 20% was enough, so it wasn't working. Our metaphor fell short. But, we're like, okay, we're not particles. We have memories. I'm not just going to suddenly start shaking, with my left hand. Like, that's muscle memory. It's going to take me a little time to turn over. So I took that model. I put in a little bit of memory in there. Now it's a parameter. I can say, people will remember some number of past transactions. We went back to our original experimental data. I ran the model with a bunch of different memory lengths and said, okay, what's the memory length that best matches our experimental data, our observations? Make a new prediction. We said, okay, with this particular population, our experimental group, we estimate a memory length of this. We think a committed minority of 24.2% should be enough to overturn an established convention. Lo and behold, 24.2% was enough. Well, 25%. I don't think we ever got a 0.2 person in our group, but 25%. So we make some predictions and we're tweaking our parameters. You can get a prediction of 40% if people have longer memories. You can get a prediction of 10% if people have very short memories. So we're like, the more parameters you add, the more wiggle room you have, the more degrees of freedom you have. But that's an example of how we can start with, maybe inspired by these physics metaphors, and modify the models. But there are a lot of things throughout social science that end up having the same math and principles of other stuff. So Yes, sometimes, if it works, be careful. I think there was one more question. I'll give a short answer.
I can save it for the last one.
Okay, don't forget to bring it back up. Maybe I'll answer it along the way. All right, I'm going to jump back into things. So now I'm going to talk about how I actually do this. I'm going to talk about modeling group decisions. So I'm going to give you a research agenda, and I'm going to give you like the TV-friendly version of it. You know, it's very clean-cut story. There's a lot more messiness than I'm letting on to right now because I'm trying to give a narrative here. I'm trying to make a claim about certain history. I have a model. I'm trying to convince you that the data fits my model. All right, so just to review the problem that I'm trying to solve is that I've got a committee that must reach agreement on a complex decision. Your product to design, you're trying to agree which features to include or exclude, policy, which features to include or exclude, how much of the features to have. So my scientific question, my explanation question is, why do they reach impasse when agreement would benefit everybody? This is the thing I'm trying to explain. This is something I've observed informally, casually in the world. It happens. I teach negotiations. I get a lot of casual observation of like MBA and master's students trying to negotiate, and I know they could reach agreement because I set up the scenario, and then I see them fail to reach agreement, and we can ask why. But it also comes with an engineering question. I'm really curious what you think about this, Ali, which is, how can we optimize outcomes? So once I understand why people sometimes reach impasse, fail to reach agreement, then I can start designing interventions. I can say, okay, well, I understand why people fail to reach agreement, so let me change this thing to help them better reach agreement. That is my engineering goal. Optimizing outcomes can just mean reaching agreement. It can also mean reaching socially optimal agreements. It can mean reaching agreements that, you know, reduce net zero while also maximizing innovative potential and not hurting the economy for rich people, like whatever it is, your multidimensional thing you're trying to optimize. This is our engineering problem. So what do we know about this problem? Well, we know the entire field of psychology tells us something about how people behave. And yet somehow in practical terms, we know almost nothing to the answer to this question. We have some ideas, right? So there's some psychological behavioral research that says when people are more pro-socially motivated, so thinking more about the social good versus more egotistically motivated, they're going to engage in more collaborative behaviors. Do those collaborative behaviors lead to agreement? We don't know yet, but yeah, probably we're going to connect some dots here, so maybe get people to be more pro-social. We know that when people share more information, it can help them solve problems better. So you need to get that information out on the table so that you know what people want so that you can reach agreement. And yet, we actually have no idea how to optimize outcomes. So the crazy thing about social science is we know a ton about humans and their psychology and social networks and how information flows in their behavior, and yet we also know almost nothing. And so we know a ton in absolute terms, but we know almost nothing in percentage terms, which is, say, of all the things we could ever know about humans, we know like 0.001%. That's a ton of knowledge, decades and centuries of all sorts of science, and Plato was helping us understand human nature, and yet it's not enough. So that's what we know. And then specifically, there's most of the research on here, as it happens, has been done by psychologists, really looking at the individual behavioral perspective. We know very little about the group, those structures. How do social networks shape things? How to group specific behaviors? So the thing about collective intelligence is that collectives display unique properties that are not found in the individuals. So wetness is an emergent phenomena of water that is not found in the individual water molecules. Liquid is not found in individual water molecules. Gas, solid, water can be ice, it can be liquid, it can be water, it can be gas. I should say H2O can be ice, it can be water, it can be steam, solid, liquid, gas. You will not find any of these things in the individual molecules. So like matter, where the individual molecules start to display uniquely group level properties as we look at the larger scale objects that we can see and touch, so do groups exhibit uniquely group scale properties that can't be explained in terms of individual behavior. So collective intelligence is that perspective. It's looking for group scale properties. And while we know a lot about individual psychological behavior, we know next to nothing about how groups behave, except there are some case studies. People go and they look at the UN making complex decisions, and they write really detailed case studies. So I can look at that and say, okay, sort of descriptively, narratively, how are people doing this? Okay, so that's what we know. Here's what I'm going to try to do. I'm going to try to do something at the collective level. I'm going to try to come up with a model that captures the uniquely emergent behavior of collectives. This is going to get technical. Don't worry, you don't need any of this. I'm just illustrating how I think through formal models. So I'm missing some things too. Let's say you have some number of people, n people. It can be 5, it can be 10, it can be 154, or however many people there are in the UN. Each negotiation has k different issues you're trying to decide. Will we include this feature? Will we include this feature? Will we include this feature? All of the different things you need to reach agreement on, the different issues or topics. Each issue has a bunch of different possible outcomes. We could do this with low-income housing. We could do that with low-income housing. We could do this with green space. We could do that with green space. Different outcomes for each issue. And I'm going to define a proposal. I'm going to put a proposal on the table and say, fellow UN members, I propose we do the following thing to solve the climate crisis. A proposal is a combination of outcomes for all issues. So I'm going to say this for green space, this for low-income housing, this for maximum building height, right? This for, you know, oil usage. I don't know. I'm not a climate scientist. So I'm going to make a proposal. And then finally, this is sort of a bigger assumption. These are all pretty straightforward, I think. Although even them, they're problematic. Not every negotiation is so carefully defined as these issues, these possible outcomes, right? But we're using this model to try to carve up the space, to get any grip on this complicated situation. And each person gets a fixed payoff for a proposal. It's a big assumption, but it means if I put a proposal in front of you, I put another proposal in front of you, you can unambiguously tell me which is worth more to you. You can numerically value each proposal. Subjectively, you don't have to agree on the value of proposal. How much do I like, you know, this color of things? I'm going to give more points for orange things than black things, right? Totally subjective, but the assumption is that people can quantify their subjective preferences, which is at least what we teach our MBA students to do. I don't know if any of them actually do it. And then, so this is the scenario. This is how I model a negotiation. People, issues, outcomes, payoffs. And then that's the setup. Now you sit down at the table and you start negotiating what's going to happen. My model of negotiation is that a negotiation is a sequence of proposals. I think that's a pretty easy assumption. You come in, you make a proposal, everybody says yes, you're done. A sequence of length 1. But if they don't say yes, someone's going to make another proposal. And then someone's going to make another proposal. Someone's going to make another proposal. I'm not thinking about what people say. I'm not thinking about the emotional temperament, the cultural backgrounds. I'm not thinking about whether they're pro-social or egotistical or sharing information freely. No, I am saying that what we need to isolate is the sequence of proposals, and we can study the properties of that. So, okay. And then this, now I can take this model. I can actually set this up computationally. This is precisely enough to find. I can set up a little computer simulation of different negotiations. And I can model different assumptions about where this sequence of proposals come from. Maybe people are just randomly shouting stuff out. I can model random sequence of proposals. Maybe more likely, someone makes an opening proposal. Someone else modifies that proposal. Someone else modifies that proposal. So you're just gradually modifying like an evolutionary algorithm. There are other plausible models you can come up with, but you can take these different models, you can run a computer simulation, and you can actually show, using this computer simulation, that there are features of the negotiation scenarios. Now we're finding a mathematical similar shape. There are features of the negotiation scenarios that can be defined formally in the same terms that we use to define computational problems, constraint optimization algorithms. How can I solve the traveling salesman problem? How can I, figure out how all the different computational problems can be complex in certain technical ways. It turns out that negotiations can be complex in the same way that computational or mathematical problems are complex. We can figure that out with the simulation, and that gets us to a hypothesis, which is that negotiations which are computationally complex are more likely to reach impasse, even when there's a large zone of possible agreement. When there's a lot of different things they could reach agreement on, which is traditionally what people would think makes a negotiation easy. Lots of different ways we can get to yes. Even if there's a lot of different ways to get to yes, if it's computationally complex, they are hard to find. So that is a hypothesis, and I actually now have run an experiment to test this hypothesis. So I basically come up with 2 scenarios. Now remember, my model is about how people behave. My model is about how people negotiate, about certain assumptions about who's making what offers and when. The implication, the prediction, is that this type of negotiation will be less likely to reach agreement than that type of negotiation. I'm not worrying about all the stuff in between. It's like the trajectory of the projectile. I'm only worrying about where it lands. And if I can really accurately predict where the projectile lands, I'm going to say my model is pretty good. So if I can really accurately predict which negotiations end in impasse and which negotiations end in agreement, I'm going to say my model is pretty good. All right. So I designed an experiment. I actually built like a web game where people come in, they do a product design negotiation where they're trying to agree on what to include, and these are the points you get for each thing you include. It's a little game. They get a chat room here, so one person really wants fast charging, one person really wants an ultra thin laptop. They can make proposals, right? They can see, what the proposals are being made. They can vote on the proposals, and they keep doing that until everybody votes yes. So my theory has sort of guided me to what to pay attention to. I'm now going to design an experiment to extract the type of data that I think is useful. And we ran this experiment, and it turned out that the more computationally complex negotiations were less likely to reach agreement than the computationally simple or easy negotiations. So I'm going to say that's like predicting where the trajectory lands. I've probably missed a lot of really important features about human behavior, but this is, my model's pretty good, I'm going to say, because it's got predictive accuracy. I want to tell you a little bit more about how I got here, because I skipped over the journey. So I started with some data. I was participating in a negotiation. I was a student in a classroom doing a simulated negotiation, a gamified type negotiation. And I thought to myself, this feels a lot like solving a computational problem. Just my lived experience of working with other students. So I've got my data, I've got my feelings, I'm analyzing it. I'm saying this data seems like it's the same shape as this computational type thing. I'm coming up with a theory, a model, right? I'm now coming up with some implications of that model. Now I'm not collecting more data, I'm just remembering. I've been a human, I've negotiated before. I'm using my experience of negotiations on top of this initial time when I was sitting at my desk doing an online game. I'm using my experience of negotiations to refine my model. The model I just presented to you wasn't the very first thing I started out with, but it was what I ended up with. Then I'm going back, I'm coming up with a new refined theory, then I'm running an experiment, and then again, I'm analyzing. I'm going to do more with this. I'm not done. I'm going to keep refining. I'm going to keep iterating, right? Okay, so that is more or less what I did. Now, there are some major limitations to this. You might be asking, like, is this real? Like, I'm playing online web games with people clicking tick boxes to include or exclude certain features of a negotiation. Is it real? Is this actually going to help me understand people in different cultures and time zones in different laboratories, maybe? Absolutely. These are real people playing a real web game, right? Oh, no, but seriously, if you can even predict, the world is so complex. People are crazy. They're so hard to predict. If you can predict outcomes for real people playing a real web game, that's pretty good in social science. But then we try to expand from there, and that's kind of where the future goes. So now I'm going to put this model to work. Now I have a theory, I have a framework, it tells me what to pay attention to, I have some ideas, I know there's some limitations, I've looked at my experimental data, I can see that the broad predictions are right, but people are doing a lot of things I didn't expect. They are searching kind of randomly, they're sharing half proposals, it's not always a complete proposal. So now I'm going to do a little bit more. I'm going to, the next thing I'm going to do is I'm just going to observe some people negotiating, and I'm going to take notes. I'm going to go back to my sort of verbal qualitative narrative description, but I'm going to do that a lot. And then I'm going to try to quantify it. So I'm going to keep feeding back between observational and more experimentally controlled data. So what am I actually going to do? The first thing I'm going to do is I'm going to try to model not people playing online games in this really constrained environment. I'm going to go back to my starting point, which is classroom activities. Still kind of a game, but if I can model people in a web game, maybe I can model people in a classroom. So step one for me, putting this theoretical framework to work, is to model classroom behavior. So I'm going to collect some data. I'm already doing this. We're watching people, we're video recording people negotiating in classrooms. I'm also running workshops online so I can get good Zoom data. I'm going to analyze it. My theory is telling me what to look for. I'm going to look at that trajectory of proposals. I'm going to try to see if I can predict who's going to make what proposal when. I don't know what I'm going to find yet. At some point, I'm going to revise my theory based on whatever I observe. The data always speaks the truth. So I'm going to observe real humans doing real things in a kind of constrained classroom type scenario. So but I think we have a clear path to maybe modeling MBA students. Ultimately, though, MBA students, when you do these scenarios, they like all sit down around a table, they get 90 minutes, they're given the roles, they're given the score sheets. Okay, you have 90 minutes to reach agreement. That is hopefully not how policy is getting made. Sometimes that's not. Sometimes that is how policy is getting made. But policy is getting made. People are exchanging emails. They're forming coalitions. They're reading the news. They're having secret back channel discussions. Like negotiation is happening in so many different ways beyond just like, here's my proposal, here's my proposal, here's my proposal, right? So after we model classroom behavior, I'm going to try to model negotiation in networks. That's not quite all the messy reality, but I told you networks are mathematical structure that are really useful because there's a ton of good theory on diffusion of ideas. So if I think the sequence of proposals is important, and my experiments so far have told me that's a useful way of looking at things that has predictive accuracy, then I can look at how those proposals spread in the network. And I can bring in existing social science. I can start matching my negotiation model up with existing models of information diffusion. And that's still going to be a relatively simplified approximation. I don't know what step 3 is. If I can get through step 1, that's going to be amazing. If I can get through step 2, I'll probably be nearing retirement. Maybe like my grad students someday will do step 3. But we're just gradually loosening our assumptions, relaxing our assumptions, and getting messier. All right, I have just a few more minutes left. I'm going to talk about the future of all of this. But before I do that, take another sip of water, give you a chance to ask some questions or comments. Yes?
How did you decide when you made the observation that this was something to pursue? Like, because in the beginning you mentioned that science should be useful in a sense. So when you were observing that this looks like
computational problem, yeah.
So how did you decide? How did you connect that observation as a valid scientific research agenda?
With the computational complexity, or just how did I get to even this engineering question?
That observation, how did you decide that was something to pursue? Because you make
I don't know. So we have a phenomena. A person has an idea pop into their head. I don't know. I don't know where inspiration comes from. It's something I've thought a lot about. I'll tell you though, I mean, priming. I'm a practitioner. I do mediation. I've done a lot of trying to facilitate people in groups to reach agreement. So, I'm primed a lot to already be thinking about that in very careful terms. And then I'd been reading papers already that were connecting computational complexity to group problem solving in other areas. So I'm already primed to think negotiation is actually a group problem solving thing. Because of my perspective as a facilitator, I'm already viewing it in these collective terms. I'm not thinking about it like a psychologist. I'm taking that macro perspective. And in other areas of social science, people have found computational complexity a useful tool for explaining and analyzing macro perspectives on group solving problems. So once you get that, you say, okay, maybe this is useful for this group solving this type of problem. It's kind of a baby step when you put all these things together. And I've been reading all those papers and thinking a lot about that while I was doing this negotiation. For all I know, I had read the paper and then gone into the negotiation. I don't know, it just all mixes around in your brain and out come ideas. I honestly don't know. That's why I wanted to give this slide, because Bruno Latour has some cool stuff that goes into like how science actually happens. Like we can come up with all our grand models of, data, analysis, model, theory, explanation, but in reality, like it's humans doing things, trying to solve problems and having ideas and arguing with each other. So it's Newton getting paid by, I don't know, the British or French government or something to build weapons of war, right? So there's all these human things. I'm forcing it into this nice, useful narrative, because then that model I'm generating of how science works informs my practice. I now have predictions. These types of questions will lead to useful engineering solutions. These types of questions won't. It's a very personal thing, though. Yeah. Other questions? Before I wrap up, I'm going to tell you what I think the future of social science could be.
Sorry for my bad expression. English is not my real language. So you were telling us about the social science coming into use the theorems or the models of those hard science kind of. What do you think about applying something different, like does the theorems or the the end thing could be like more flexible, like in social science.
I'm not sure what you mean about more flexible.
The model, like me being an anthropologist, it is like it gives me a goosebumps to think about a model in a really complex situation, right? I know that you already say that. For me, coming with a model to explain something about humanity is difficult. But what would you say that, about coming with a model that is flexible, that is not
Yeah.
set in stone?
This is tough. So the more flexible your model is, the more parameters you put in your model, the more likely you are to be able to figure out the right parameter combination to predict what you just observed, which makes it less useful because you want to be able to reduce the number of parameters to simplify the space, to simplify the understanding. I don't have a good. It's hard to put my finger on. Because it goes back to, remember the feather and the bowling ball predictions. If you have a really loose model, you can predict almost anything. So no matter what happens next, you say, yes, that's consistent with my model. Models must be falsifiable. You have to be able to prove your model wrong, or at least have it fail to predict the world, is what I mean by prove wrong, or it's not useful. Because there are some predictions that come right, you say my model is useful. There's some predictions that turn out wrong. That's where you know to refine your model. So the looser your model gets, the less likely it is to be wrong, and that's actually not good. But I want to, in terms of the complexity of people, I want to say I don't know anything about quantum physics, but I know it's way more complicated than Newton's 3 laws. So even physics deals with this problem of increasing complexity as you get more and more refined. I talked about non-Euclidean mathematics, this notion that parallel lines can actually get closer even though they never touch. Like, that's kind of mind-bending and not at all consistent with how we experience the world. Is not a simple parsimonious model, but it turns out to be more useful at really large scales or really high energies and sizes and things like that. So I think the fact that some of this stuff is uncomfortable and mind-boggling and impossible to imagine is not at all evidence that it's not the way to go. It's just evidence that humanity's even more complex than quantum physics, and quantum physics is hella complex. Yeah, Lorelai.
So I'm interested in the fact that you took an experimental approach when looking at this, and I think it's fairly well known that a lot of experiments in social science tend to be like a little bit fake. And the reason I'm bringing this up is because you mentioned that you're also a practitioner, and so I'm assuming that you also have a lot of data coming from observation. And so I'm curious how your experimental data sort of like matches up with your observational data when it comes to your work.
So I want to challenge a few things there. First of all, experiments are not fake. These are real humans playing a real online game, reaching real conclusions and getting paid in real money. They do get paid more if they reach agreement. They're incentivized. When I do the MBA class simulations, these are real MBA students completing real class simulations for real bragging points that we're not paying our students, right? When I mediate, these are real people sitting at the table having real conflicts with their real neighbors. And it's not that different from my online experiments. The ethics of recording are, of course, very different. But remember, an experiment is something you can do over and over again. So my mediation sessions are, for data collection purposes, an experiment. I am repeatedly sitting down with people in conflict and running the exact same process. And when I'm mediating, I am controlling things about as much as I'm controlling things in a lab experiment. I walk people through a very specific controlled process as a mediator. That doesn't make it fake, it just makes it engineered. And it's engineered because we have intuitions from experience that tell us what works and what doesn't work. And yes, all of that life experience is informing how I choose to set up the experiments. But also, I talked about wanting to loosen up my data a little bit. Experiments can also be observational, like that mediation. I could bring in real people to have their real conflicts out on Zoom and record it if I get the ethics approval. And that would be real people, real conflicts, but it's replicable, so it's an experiment. So I challenge the notion that experiments are fake. They're just constrained And it's precisely because we're controlling all those different variables and reducing the messiness that we're able to get traction, and then we gradually move out from there. Yeah, one last question, then I'm going to wrap up.
Following up on Nicholas, so you still have the story of how we do science, which is around like the metric for success is finding a formal model which kind of predicts those situations.
I would say the metrics for success is predictive accuracy. I tend to find that formal models give much better predictive accuracy than verbal models.
One way to get this kind of predictive accuracy is to start predicting things about the systems or the games you set up, and less about the people involved.
Yeah.
And it seems to me like you end up studying the systems and the formal models and like the games you built, and less so like the people.
Absolutely, I love that. That's a great way of reframing what I was trying to say. I'm not studying individual behavior from the collective intelligence perspective. I'm studying the groups, and you're exactly right. I'm not studying all the detail and color and noise and sound and taste of the projectile moving. I'm just looking at where it lands. And maybe, I don't know, its peak height, right? So exactly, it's exactly that. We are looking at outcomes, we are looking at systems, we're looking at what the model tells us important. And for me, model tells me sequence of proposals is important, nothing about people's moods or emotions. Moods and emotions are going to become important at some point. You're only going to get so far in your predictive accuracy with this high level. Let me wrap up. I've only got a few minutes at this last bit. I'm going to tell you where I think this is going, and then we can talk freely. All right, so I worked the title of the session into my slide. All right, so what is the future of social science? So it's literally this, gradual refining the process. So I have, and this is more practitioner derived, but I find it useful, a general conceptual model that I use to divide up the world of decision making, specifically group decision making, but also individual, which says that there are 4 things. You are going to define the problem. You're going to identify solutions, brainstorming, right? You're going to evaluate solutions. So that's like how many jelly beans are in the jar, how many jobs will this policy create? And then you are going to choose solutions. That is the negotiation. And if everybody agrees on the payoff function, we want the policy that minimizes carbon emissions, step 4 is easy. But usually people have very different preferences and priorities because the world is complicated. So this is my general kind of model of the world. So we have pretty good science of how people form numeric opinions, numeric beliefs, although there's huge limitations of that I glossed over in my story about universal laws to Eric earlier. There's mess behind that as well. There's not a ton of, as far as I know, on group defining the problem. There's some stuff on identifying solutions. There's next to nothing on negotiation at the group level, but I believe I have charted, a decent agenda for getting there. So my agenda right now is get a really good model of people only doing numeric estimates. Don't worry about the negotiation. Get a really good model of people only negotiating. Don't worry about numeric estimates. Get a really good model of people brainstorming. Don't worry about evaluating. Don't worry about picking. We're isolating different subcomponents of human behavior of these systems to study them in their pieces, the way in a laboratory we're going to study this particular material before we try to build a bridge out of it, right? We're isolating the pieces, then we're going to maybe someday put them together. So I think we're not too far off from mixing evaluating solutions and choosing solutions, or identifying solutions and choosing solutions. That would be like the network models of innovation plus the negotiation, right? As these models of individual isolated things get better, we can start combining them together, and then what can we do? Well, we can come up with a really, really good model of MBA students in a classroom, and then maybe committees more generally. The smaller, in a sense, the simpler. That's not always true. I'm painting a narrative today. As we get better at understanding committees, we'll get better at understanding organizations, which are essentially big committees of committees, right? We're expanding outwards. As we get better at understanding organizations, we can get better at understanding nation states, that policy-making thing we really care about. How can we think about UK's innovative policy, which is going to be a mix of, what organizations are doing in government, in industry, as well as what politicians are doing, right? It's getting more and more messy. And then ultimately the world, and this would be, a science of history and a science of future history. So that's the basic idea, is we're just gonna get more and more complex, more and more detailed. We're going to keep bouncing back and forth between our data and theory until we can come up with all the universal laws, and then we can say, okay, what are the parameters of this particular time period, this particular culture? Like I said, I am extremely optimistic. This is hugely ambitious. Sometimes I lie awake at nights thinking it's never going to happen and I'm wasting my time, but I really care about the engineering problems, and so I'm at least going to try. All right, that's my bit. I know I talked a little more than I said I would. Thank you all very much. I will hang out and chat for some time now. Actually, I'm just going to leave.
Any more questions, comments? I have one, which is, if you, let's just say that the world government approached you as like, hey, you know, we want to draw on your expertise to create an institution or a tool to improve global democracy. What might that tool
I have no idea.
Okay.
And this is why I'm giving this talk. This is why I have to constantly remind myself to be optimistic. And this is why I tried to emphasize that, like, what we know is almost nothing, even though we know a ton, right? And this is why I am a scientist and not, say, you know, a fellow here at Newspeak. Also because life takes you in, you know, history, chance. I just happened to live other places first. But I'm a scientist because I kept asking, you know, how can I do the greatest amount of good? Okay, I can go out and I can do some work in the world, or I can be a volunteer organizer and, you know, organize other people to do things, or I can, you know, become an activist and try to design systems and engineer things. I'm like, we actually have no idea how to do any of this stuff. So I've decided to become a scientist to try to figure out how to do this stuff. I'm also a practitioner, so we don't let the perfect be the enemy of the good. So if the world government did call me, and actually, I got the European Commission emailed me and said, hey, can you write us a report on collaborative policymaking? Tell us everything best practice. And for them, they mean mostly collaboration within the 27 members of the European Commission and, you know, the other staff members, but also to some extent collaboration with citizens. So I went and I got a research assistant to go search as many papers as we can. I got an AI tool to try to summarize and thematize them. And I wrote down everything I could figure out that we know, and it wasn't a lot. And then I wrote a whole bunch of stuff. I said, look, I want to give you useful things. I'm also a practitioner. I'm going to write some insights from practice. I know a lot of the stuff that I do as a facilitator works in practice. What I am trying to figure out right now is whether it works in theory. So I think we're like, if this is like the trajectory, we're somewhere up on the first floor right now. Yes.
Part of the ongoing conversation or some of the challenges that I feel around science in a like applied capacity, or the extracting knowledge from science to put towards decision making, etc. Some of the conversations around that is a big challenge, is that we often underappreciate the role of emotions, narrative, commonly held beliefs, like some of that, softer, fluffier, gooey stuff, if you will. I'm curious in terms of your work here to basically, simplifying it in my head, like more systematizing, mathematizing some of the social science research, if you're at all concerned that it will go down a similar trajectory, or if we're going to similarly end up underappreciating or masking some of those more emotional, individual qualities, personality-based things that heavily affect things that happen at the collective level too.
So what are my two options that I'm choosing between?
I think it's more the extent or the gradation of like the more qualitative aspects of social science research. Like, how much do we hold on to that in this future that is leaning more heavily, it seems, into the more quantitative, the more like scientific mechanism.
And this is my future. I don't think this is my colleague Jen's future. This, might not be Eric's future. When you say, let me see if I can try to capture the gist of your question. You're talking about how much are we losing, like the emotions and the qualitative stuff. Are you worrying that by formalizing, by mathematizing, by doing like a sort of like physics of people, we're losing the essence that makes us human?
Yeah, losing the essence that makes us human, or I think part of the pieces when it comes to like fitting phenomenon into a model is that we oftentimes focus on the parameters, weights of the parameters. But in my model of the world, I feel like there's so much richness that is in like the error term that is oftentimes overlooked.
Yes. The error term, so the difference between what my model predicts and all the wide variance of outcomes. I talked about things being true in the average. So I did this experiment and we predicted, well, I simplified things. We predicted that this group would reach agreement more than this group. We also predicted that this group would reach agreement like 78% of the time and this group would reach agreement like 62% of the time. Neither of those numbers were accurate. We got the order correct, but there was huge error in our predictions on other outcomes. So we know our model is both useful and wrong, right? So there are huge elements that we are simplifying away. And I think in terms of whether it's important to capture meaning and emotion and personal identity and experience or whatever those things mean, I don't even know, will be borne out in the question of whether our models are useful. If models without emotion and meaning and identity are useful for a particular case, then you don't have to worry about it. If your models are consistently failing, maybe you need to incorporate some of that stuff. And there are other people in this space working on these things in similarly like quantitative or formalized ways. There are people studying the contagion of emotion, emotional contagion, and they're using mathematized social network models, and they make basic assumptions about like over time, I gradually become more similar to the people around me. That's a pretty reasonable assumption that has been shown to be true in a wider range of circumstances. Maybe that's because I have agency and free will and I like my friends and I choose to become more like them. Maybe that's because the world is deterministic and there's a force of gravity pulling me to my natural place. Like, we're not getting into the why of people becoming more similar, but let's say we make assumptions that people become more similar over time. Now we can derive certain principles about emotional contagion. So my answer is always going to be either your model has predictive accuracy or it doesn't. And if it doesn't, maybe the things that are missing are some of the things that you just mentioned, the so-called qualitative stuff. But I don't believe in this qualitative-quantitative divide. There are models, there are predictions, there are analyses, there are things that are useful for certain projects and goals and things that are not useful. There are lots of different ways of theorizing. There are lots of different ways of analyzing data, and the whole qualitative quantitative thing, I don't personally find it all that useful. Yeah.
So following up on the comment about predictive accuracy, which like for you is a way to sort of understand that your formal model is good or bad. In some fields, like say natural language understanding in computer science, there are these recent artifacts that have emerged that are very, very good at predictive accuracy on any sort of natural language understanding task that had existed for decades before. But those models are have trillions of parameters or billions of trillions of parameters, and they don't really look like the one that you described. And my question is sort of like, for you, is a large language model a formal model or not?
No.
Okay.
Because you don't have a model. It's a prediction. There's a lot of different ways to get prediction, and data science, machine learning type techniques are incredibly useful for that. But there's no model, there's no representation. A model is a representation of how we think the world works. And maybe there's debatably some potential representation in the large language model parameters, but that's not really what's going on with predictive accuracy. Predictive accuracy just saying, hey, this looks like this other thing, so I'm going to assume the outcome is the same. It's making some assumptions about what features are important, but what I'm talking about are what's known as generative models. So my assumptions are generating... Right, not generative AI. Right. So thank you. Generative AI, new term, generative models, less common term that I find very useful, so I use it. Go back to my model of like physics or negotiation. I said these assumptions, it moves at this rate and falls in this way and this thing, and therefore these assumptions generate a parabola or a hyperbola, or these assumptions generate groups that reach agreement and then groups that don't reach agreement. And I have a very good friend, Abdullah Almatuk, who has done a ton of work on virtual laboratory stuff. We've collaborated together. They work at MIT. They're also in the collective intelligence space. Funny thing is, I think they do very similar stuff to me, but they're in a different department. So their papers come out looking very differently. The traditions and norms are very different. They're actually in an information technology department, but we're both studying collective intelligence using formal generative models and laboratory experiments. So they very much describe what I'm putting forth as so-called a feeling of understanding. All of this stuff I'm talking about with models and explanations and generating and premises leading to conclusions, Abdullah argues that just gives a feeling of understanding. For engineering purposes, all that matters is the ability to predict. When I build with this material, how will it do under this temperature, over this length of distance if I'm building a bridge and so forth. And I think Abdullah is true. If I can predict all the things I need to predict, I'll be able to do the engineering I need to do. However, I speculate wildly that that will have limited utility, that the ability to do these science trajectories requires having generative models because it gives us ideas of what features to pay attention to. It helps us figure out where our error terms might be coming from, which you can't necessarily tell. But that's something that we will see over time. It might be all about data and machine learning and no feeling of understanding whatsoever. But I also like a feeling of understanding. So if we get to the point where machine learning has solved all our problems, I can go back to being that Aristotelian, like seeking truth for the divine beauty of the universe. And that you definitely need explanatory models for. Yeah. There is no beauty in purely predictive efforts. Yeah.
So what, from your practical experience, even though the model isn't super accurate, what helps groups reach agreement outside of making the issues less computationally complex?
Oh, well, so first of all, that's not even the most useful thing because you can't change your negotiation scenario. You can't be like, oh, let's have a less computationally complex negotiation. No, the negotiation you're dealing with is what it is. And again, we derived predictions about computational complexity. What we're really interested in is my model of people exchanging proposals and the assumptions that I didn't get into today about how people choose which proposals to offer next. That's what I really care about. But also, I don't know yet. We have a lot more work to do before we can derive interventions. Being more pro-social, less egotistical, sharing information, all the stuff the social psychologist said. We're still trying to figure out interventions.
Yeah, I have similar questions like our currently usually our goal is to the model to generate the accurate prediction of the following things, but how do we harness the model to generate some effective action or wise action to the situation that can help to change the situation to enhance the model to have very strong application.
So are you kind of asking how do we use models to generate interventions?
Similar is not generate prediction, but generate action.
An action.
What kind of action should be done? What kind of action is wise?
So how do I use the model to come up with, say, this will get you to agreement and this won't? Yeah, so the model has all sorts of predictions. One prediction is that different negotiation scenarios. We also model different negotiation styles. What if I make this type of proposal? What if I make that type of proposal? So we can use the model, now that we've determined it has some limited fake predictive accuracy, we can use the model to say, okay, what if I as a facilitator come in and do this and I can simulate that? What if I as a facilitator come in and do that? I'm being vague and hand-wavy because we haven't done that research yet. But that's it. Once we have a good model of how the world works, we can, in that model, experiment with different things and say, okay, I think this behavior will get groups to agreement. And of course, you've got now more experiments, but once your experiments work pretty well, you start to get more confident. Yeah.
This is the tricky thing here. Usually, it's we human propose some possible action, and the model can tell us what kind of the outcome or prediction of your action.
So I'll give you, yeah, exactly. So I'll give you an example from my other line of work, which is more developed on belief accuracy, the numeric estimates. One thing we found is that in groups of people, when rates of speaking are very unequal, so some people talk more than others, that behaves mathematically like a centralized network. And I said that in centralized networks, the central people are more influential. So you're more talkative, you're more influential. I also said that the average of a group of people is more accurate than a randomly selected individual. So if you have one person who's dominating the conversation, you're getting the wisdom of the few, you're not getting that wisdom of the crowd average. So that's some statistical stuff. We got some experimental data, some, we've done a little bit of circling back and forth already. So that now leads to the conclusion that one way to get a group to come up with more accurate beliefs is to ensure that everybody contributes equally to the conversation. Is that an example of the kind of action that you're looking for?
Yes.
Okay. So that's how we do it. We say, well, the model says this is bad and this is good, so let's try to get us into the good state.
Yes, it reflects the model give the judgment or the evaluation of the proposed action.
Yeah.
Is that possible that that's a model to propose action? Is it possible to let the model to propose some action?
Oh. The model doesn't do anything. You do things with the model. You analyze the model and you think about the model and derive conclusions from the model. I think in all of this, you are doing the work. The model is useful in that process. Yeah. All right.
Perhaps time for one more question.
All right.
No pressure.
Maybe like a potential way to apply what you kind of your theory around computational complexity and how easy it is to reach consensus. Let's say if you're a negotiator and then you're in a condition like a time-sensitive condition, and then you have to reach agreement in a group of 100 people in say 2 days. Then maybe if you have the model, like I don't know exactly what your model can predict, like how precise it is.
Not very.
But then maybe you can inform things like, oh, is it better if I break down this big group into smaller groups of this many?
Yeah.
And then that will take how long to reach a consensus within each group. And then I take one person or the idea from each group and then put them together and then do a second round. So like it sounds like would be a really interesting application.
There we have it, the final comment of the night. Yes, you can use these models to ask questions like, what if I break the group up into smaller groups? Will they reach agreement faster? What if I do this? And there are some mathematical techniques that you can say, like, I have an optimal point. Can you help me find the parameters that will get me to the optimal point? I already told you I'm not good at math, but that's it. That's it. You can use the models to test interventions and solve your engineering problems. Thank you for that final word.